Tidal wavelength does not equal pressure. Vertical contribution functions in their implications for mapping hot Jupiter. Authors Ian Dobbs Dixon and Nicholas B. Cowan. First authors Institution Department of Physics, NYU Abu Dhabi. Status published in APJL. Open access. The phase curves of transit planets reveal the longitudinal from day to night variation. When observing with multiple wavelengths, they further tell us the information in the radial direction. Different wave bands in principle probe different pressure depths in the atmosphere. Since different wavelengths have different opacities, the ability to absorb and scatter photons. However, the opacity is determined by the local temperature, pressure, and gaseous composition, and there is no reason for the opacity to hold constant across the planet, as we will see later. In today's paper, the authors address this important yet challenging issue when it comes to interpreting the multiband phase curves. Trends do not fit with one-dimensional models. When considering a one-dimensional atmosphere, as has been widely used in modeling, we can predict which wavelength will probe deeper into the atmosphere by examining their opacities. Water is one of the main infrared absorbers. Since water absorbs more radiation at 4.5 micrometers, the opacity at 4.5 micrometers should be larger than that at 3.6 micrometers. A larger mass of overlying gas at 3.6 micrometers is required to achieve the same absorption as at 4.6 micrometers. Hence, the photosphere, where photons are mostly absorbed and emitted, is deeper at 3.6 micrometers than at 4.6 micrometers. The radiative cooling operates less efficiently as the pressure increases, hence we know that the day-night temperature contrast should be smaller in the deeper atmospheres. Therefore, one would expect the day-night temperature contrast, represented by the observed phase amplitude, to be also smaller at 3.6 micrometers than at 4.5 micrometers. In addition, the phase offset, how the hotspot being shifted and normalized amplitude should be anti-correlated, with large amplitude phase variations having a small phase offset due to the inefficient heat transport. However, neither of these are observed. Figure 1. Phase offset versus normalized phase amplitude for 7 hot Jupiters. Blue is 3.6 micrometers and green is 4.5 micrometers. Each planet is denoted by different symbols, and the two wave bands for a given planet are connected by a line to guide the eye. The normalized phase amplitude is always greater at 3.6 micrometers than at 4.5 micrometers. Figure 1 collects the data from 7 hot Jupiters for which we have multi-band phase curve observations. The z-axis shows the normalized phase amplitude, the flux contrast of the dayside and night side divided by that of the dayside. One can see that blue points 3.6 micrometers are always to the right of green points 4.5 micrometers for each planet, meaning 3.6 micrometers observations exhibit larger day-night contrast. According to the previous argument, we would naively expect the blue points to be to the upper left of the green points. Predictions from a 3D radiative dynamical model. The authors explore these phenomena by running a radiative hydrodynamic simulation of a hot Jupiter, HD 1890733b, assuming thermochemical equilibrium. The model produces theoretical phase curves with greater relative phase amplitude and greater phase offset at 3.6 micrometers than at 4.5 micrometers, in agreement with the data. This demonstrates that the opacity cannot be simply presented by a 1D model. Instead, the photosphere can be a convoluted function of both longitude and wavelength, as shown in Figure 2. First of all, the day-night temperature contrast is truly decreasing with increasing pressure in general, as we expect. Looking at the photospheres in different wave bands, we find that a single waveband probes different pressures depending on the longitude. The contribution function showing the vertical contribution to the emission flux in the right panel shows a significant contribution at 4.5 micrometers from the upper, cooler regions on the dayside relative to 3.6 micrometers leads to a smaller phase amplitude. The result is that the effective photosphere in each band does not necessarily maintain its relative position as one moves around in longitude. Figure 2. Left, the peaks of the contribution functions for the IRAC and MIPS bands, colored bands overplotted on the temperature in K grayscale as a function of pressure and longitude along the equator. The noon longitude is at 0. Right, the vertical contribution functions at noon solid and midnight dotted locations. Multi-wavelength maps are further investigation to understand how the global opacity distribution changes is shown in Figure 3, where we can see the total opacity, the absorption of all the gaseous molecules as a function of temperature and pressure. By following the same pressure across each of the plots, we can roughly visualize how the opacity changes along the longitude. Interestingly, the opacity at 4.5 micrometers increases when moving from night to day, while at 3.6 micrometers it decreases. This feature makes the effective photosphere at 4.5 micrometers higher on the day side, where the atmosphere is cooler, and hence reduces the day-night contrast phase amplitude. The behavior of opacity is due to the CH4-CO transition. CH4 is favored at lower temperatures and has strong absorption at 3.6 micrometers. CO is favored at higher temperatures and has strong absorption at 4.5 micrometers. Therefore, the photosphere at 3.6 micrometers can be higher than at 4.5 micrometers in the cool region. Figure 3. Log of the total opacity in CM2G1 due to molecules CH4, CO, H2O, and CO2 as a function of temperature and pressure at 3.6, 4.5, 5.8, and 8.0 micrometers. Thermochemical equilibrium is assumed at each temperature and pressure. The obvious feature running diagonally through all of the plots is the change in opacity as the dominant carbon-bearing molecule switches from CH4 in the lower left to CO in the upper right. Unfortunately, the convoluted photospheres complicate the interpretation of multi-wavelength phase curves. In particular, the authors show that the classic 1D assumption that different wavelengths probe different pressure layers is incorrect. It is true only at one longitude, but the order of the layers changes from one location to another. This is a complication worth tackling soon in order to construct multi-dimensional maps of hot Jupiters.